See, I think this year they just gave us like.
Your brother would disagree.
She likes spring break.
The state game.
I like spring break.
We went school.
Which I'm like coming back from spring break, that's true. Coming back.
I'm talking about
Because
these 2
school-
weeks.
Yeah. They're just like, no, we're not gonna have this issue anymore.
Not this class.
It's just like,
For a senior.
yeah.
Not in this
I
class.
thought next year looked.
Wait, next week's not like 40.
Yeah, I think it's
It's
harder
gonna be 3 weeks.
because I go hard, and then there's all the play stuff that takes up your time. Yeah, you got
I
some
don't
sports
need to
stuff.
see it.
Okay.
I don't want to see it.
All right. Hey, let's focus here. What we are now, this is the ice table lesson for acids and bases. Okay? Now, it was really important that we laid a foundation with ice table last chapter because it was easy stuff last chapter. It's a little bit more difficult in this chapter because it's more conceptual in that you've got to remember, you know, strong acids, strong bases, weak acids, weak bases, and how they differ. The reason why I say that is because you do not need to do an ice table for a strong acid or a strong base because you know where the equilibrium is. Everybody hear me on that? I already said that today, but I want to hit on that because when I give the test in this chapter, or the quiz, we'll probably have a quiz in the middle of this chapter. It's probably coming up in,
Is this a one-day class?
yes, but I am going to throw a quiz right in the middle, probably sometime near the end of this week. Maybe Friday, because they actually have a full day. Okay, does that make sense?
Yeah.
I just want to give you another quiz because there's not a whole lot of quizzes second semester since I've given a lot of one chapter tests. Does that make sense? And I don't want you to have like one quiz outlier and then not have a chance to get another crack at it. So the reason why I say that about strong acids is on a quiz or a test, a lot of times students don't know what to do when they try to start doing ice table stuff when you don't have a Ka value for a strong acid. Why? Because it's so high, it's undefined, and so they freak out, how do I do an ice table without a K value? But when they really should, for example, if I know that I have a 1.0 molar strong acid, how do I find the pH of that?
10 to the
Early. Why? What is the pH dependent upon?
concentration.
Of hydrogen. And what do we know about this? It's a strong acid. Completely dissociate. And so the concentration of my strong acid will be the same as the concentration of my H+. You see how easy that is? You don't have to do any ice table stuff. You don't have to worry about anything. It's really super easy, but students usually mess this up because we don't spend a ton of time doing strong acids, strong bases because they're pretty simple. Does that make sense? Yeah, pH, yep. Tried to erase that. Alright, so, alright, so really what we're going to be doing here then is, yes, we are going to be doing all the ice table stuff, but at the ending you add a couple more things. The reason why we want to find what the equilibrium concentration is using ice table is because that tells us what the hydrogen ion concentration is. And if we have that, we can solve what? pH. Okay? Now, you're probably not going to think that this is that important, and it isn't in this problem, but we're going to see in probably tomorrow when we get to it, we'll have situations where you have multiple acids in solution. Okay? Where I'll have 2 acids plus water, which also could potentially act as an acid too, right? In solution, you got to figure out, okay, what is the dominant producer of the hydrogen ion concentration? Because you could have one that gives a lot and the others that give very little, and so you can just ignore the other ones. Does that make sense?
You go with the strongest one?
Yes, unless they were like really close. Okay? So the very first step is this idea of finding major species. And I kind of talked about this a little bit last week. This is basically at equilibrium. what am I going to have the most of? Okay, so if we look at this problem, what is my acid? HF. The very first question that should be running through your head is,
Is it a strong acid? Yes. No.
is this a strong acid?
We can't tell the Ka.
That's true. Very good. Yes. Okay. Now, again, I would still make sure I memorize those strong ones just so that like there's another red flag popping up into my head besides just looking at the Ka value. Okay, so my major species are at equilibrium. I'm going to have mostly this left over, right? Because a lot of it's going to react. It's weak. My other major species is H2O, and the reason why that's important is because that can also act as a what? Acid.
The common major.
Okay? So those are my major species. My hydrogen ion and my F minus concentration are going to be very relatively small. And the reason why this is important is because I got to figure out which one is the dominant giver of my hydrogen ions. And the best way to look at that is to view the K values. So my Ka for this is 1, not 1. It's 7.2 times 10 to the negative 4. And what is my K value for water? Okay, so if we look at this, 1 is going to give off a whole heck of a lot more hydrogen ion. Which one is it?
HF.
HF. Okay? Now, if these were flipped, or I shouldn't say that, if this was like 4 times 10 to the negative 25th, what's my pH? 7. Okay? So what I'm saying here is, this is the dominant H plus producer. Does that make sense? Okay, once we've identified that, and that's really what step 3 is to figure out which is the dominant producer. Once we do that, we can begin the ice table process of first writing the equilibrium expression. Following? Okay, we've got the equation here that can help us with that. So my Ka, products over reactants, follow. Am I going a little fast? I'm kind of going a little fast. And I know, guys, I'm telling you right now, do not skip this, or at least make a mental note of it. You don't maybe have to write it down on a test or in your homework, but this is important because it's very possible that you could save yourself a whole bunch of time if you notice that water is your dominant giver of hydrogen, because then you know it's 7. Okay? So step 5 through 7, these are traditional ice table. Now I'm going to write the equation up here because that way I can have room for my ice. I know what I'm throwing in here. Okay, what is my initial concentrations here? How about these two?
0, 0.
Again, I didn't tell you they were 0. If they don't tell you anything about it, you can assume that. Well, you're never going to have concentration of water because it doesn't change, right? Okay? Now, which way is this going to shift? Normally we would do a Q step, right? But
It'll shift slightly right or not a lot.
okay, it is going to be right. Even though it's not it lies far left at equilibrium, we have nothing here to begin with, right? So it will react and shift right.
So can you tell that from the Ka or?
No, you would have to. We will get to certain situations where these won't be 0, but it's a little ways away yet.
So it's
But if these are 0, kept right always. Okay? So minus x plus x because everything's a 1-to-1 ratio. Cool? What would be next?
10.2 times 10 to the negative x squared minus x.
You would do what?
Plug it. Yeah, that.
See, don't go any further.
Okay.
Here's why. There was something we talked about, yes, last chapter.
5%.
Yes. We are going to do a 5% rule for every weak acid and every weak base.
So almost. Because otherwise.
That's true.
You don't need it at all. Let's say so much.
And the reason why is because weak acids and weak bases don't dissociate very much at all. So their Ka values are really small. So their change in their concentration is going to be what? Small. And if their change in concentration is very small, is it going to affect the 1.0 very much? So what can we get rid of up here?
X at the bottom.
That x. And what that does is takes away the quadratic. Ka is very small, use the 5% test. So then that's what I'm going to do here. We're going to remove x because that x is so much smaller that's not going to really change the concentration of 1. And we will prove that, we will test that out. Okay, so let's solve.
Third of 0.027.
And you're going to find that when it's a 1-to-1 ratio, everything here, that's how you find the x every time, square root of Ka. If it's a 1-to-1 ratio and these are 0. Okay? Now, again, I would still be literally just assume that all the time because that might hurt you later on when we actually have to know the difference. Does that make sense? So what did you guys get for an x? Now let me show you what the answer would have been using the quadratic. What our x would have been if we were using the quadratic. Much of a difference?
No.
Rounds actually to the exact same answer. Okay? Now, in order to make sure this is legit, do you remember what the 5% test was? Okay, here's the generic equation. Ka equal to my change, or my x, divided by my, and I put ha. Why do I put ha? What does that represent? Generically. Initial concentration of what?
On the left.
This is your acid. Hydrogen. Okay? So, then you would times it by 100. So what we're going to do, take my Ka. You guys don't remember the generic equation for an acid?
I mean, it's 1.24, so it makes it 5%.
What is this? -4 equals 0.0268 all over 1 times 100. What do you get?
Over 1, you mean over the.
Wait.
1.25.
Wait, you don't need to say in there. Sorry. No, I did kidding.
And 1 over 1.
That's the initial concentration of my weak acid. Because aren't we trying to figure out how far it deviates from my initial concentration? Because we want to say if it's a small deviation, it's okay to remove the X. But if it's a big deviation, then it's not okay to remove the X. Does that make sense? So what did you guys get? It should be less than 5%. 2.7 approximately. Okay? What that means is 5% valid. That just verifies that doing it this way is okay. Last step then, what is my ultimate goal? pH. Now, normally we would take our X, correct? Or right here. We would plug it back into here to find the concentrations of everything, correct? Well, we want the concentration of this for pH, so simply 0.0268 will give you a pH of 1.57.